Well, here I am talking to this very quiet, empty room. It's Monday, like it says behind me there. I'm going to be going through some more of Section 8. Before the break, I had introduced Ampere's Law, which, once again, just to kind of get you back into it, it says if you pick some path, and it has to be a closed path, you have to end up back at your starting point, that the strength of the field along that path times the length of the path is equal to a proportionality constant times the amount of current passing through that path, okay? The length times the strength is equal to mu naught times I. Of course, if the field varies along the path, then you have to break it up into little pieces and integrate. It becomes the integral of B dot ds. And I'd already gone through, I'd gotten to the bottom of page 24 of the note packet, which there it, the wrong way. I took Ampere's Law and tried to make it into a little step-by-step recipe. Hopefully you've got your copy of the notes in front of you. You can probably read it a little more clearly than that. I talked about how the direction of the field through a coil is given by the right-hand rule, like it shows at the bottom of the page. I had done example number 1, where I used Ampere's Law to get the field around a straight wire. And the first thing that I hadn't gotten to is problem number 2, which is to apply Ampere's Law to a very different situation, the field of a solenoid. So right there is a cross-sectional view of the solenoid. All the little dots on top are supposed to be the current flowing out toward you, and all the little X's on the bottom are the current flowing away from you, as if you would cut the solenoid in half the long way, but somehow the current managed to still flow. The field lines go through the coil parallel to its axis, left to right across the picture there. So, following the same step-by-step kind of thing from the previous page, steps 1 and 2 were to decide what the field looks like and pick a path. Well, what the field looks like is what's in that picture I was just pointing at. If that's the solenoid with the current flowing out toward you here and flowing away from you there, and the field lines pointing along there like that. That's kind of what the field looks like. I should probably clarify that what we're talking about here is an infinite solenoid, which of course, like many of the things we talk about in this class, is silly. There are no frictionless surfaces and there are no wires without electrical resistance. Well, at room temperature, there are no wires without electrical resistance. But anyhow, an infinite solenoid in practical terms means a coil whose length is much greater than its diameter. And we're not looking at a point that's anywhere close to the ends, okay? Near the ends, the field lines would start spreading out and the field would get weaker. But to simplify things, imagine that it's an infinitely long solenoid, which means that if I took the picture and slid it some distance to the right or to the left, nothing would change. So the field, as far as right and left goes, the field here has to be the same as the field here, has to be the same as the field here. Because of the you know, symmetry of the situation. There can't be any, B cannot be a function of X, okay, if the X-axis is horizontal. So that's kind of what it looks like. We're supposed to pick a path, and that was already filled in on the diagram in the note packet also. We're going to use a rectangle this time. Let's call the length of it L. Guess I need that camera just a little bit higher. There. Step 3, evaluate B dot S along the path, breaking the path into pieces if necessary, which in this case it would be. B is the magnetic field vector. S would be measured in meters. If you imagine a bug crawling across the blackboard following this rectangular path, S would be the displacement of that bug as it goes walking across the blackboard. So that's going to be dot product is the magnitude of the one vector times the magnitude of the other vector times the cosine of the angle between the two vectors. We need to evaluate that for the top of the path, and then down the left-hand side and up the right-hand side. Now, actually, I might as well say right now that this part is 0, because in an infinitely long solenoid, the field outside is 0. If it was truly an infinitely long solenoid, I've said magnetic field lines have no beginning and no end, which usually means they're loops. But the other possibility is if the field lines run from negative infinity to positive infinity, you're not going to find any end on those lines that way either. And that's what we're talking about here, okay? Now, in the real world where you've got simply a long coil rather than an infinite coil, the field outside is not quite 0. The field is just a lot weaker outside than it is inside. Remember that when you draw pictures, the strength of the field is illustrated by the density of the field lines. Where they're packed close together, the field is strong. Where they're far apart, the field is weak. Well, as the field lines go through the coil in the one direction, they all have to funnel through this little hole. They have to go through the inside of the coil. After they come out the other end, they've got the whole world to spread out into as they return from left or from right to left. And so they, like I said, they spread out, and the field is a lot weaker out there. And the longer the coil, the more that that's true. With an infinitely long coil, the field outside would be just plain 0. And so across the top of our path, the length times the strength is 0, because the strength of the field is 0. On the left and right sides, the issue is the cosine factor. Theta is the angle between this displacement vector and the magnetic field vector. Well, if you imagine an ant, some kind of insect, following this path around my picture, as it goes down this side of the rectangle, its displacement would be downward, which is perpendicular. Well, of course, out here, there isn't any field anyhow, but once it's inside, that's perpendicular to the direction of the field. And over here, where the bug is going upward, that also is perpendicular to the direction that the field points. And so nothing there either. And then finally, there's the bottom. We have to include all four sides. And the displacement of my ant that's moving along this path here, that would be the length of the rectangle, L. The field vector and the displacement vector are parallel to each other. And so cosine of 0 degrees gives me 1. And so when you add up all four sides of the path, it's B times L. So that's what's to the left of the equal sign in Ampere's law. I think I want to go a little further. Step 4, set that equal to what's on the right-hand side of the equals in Ampere's law, which is mu naught times I. Where I represents the total amount of current, the total amount of amps going through our path. And the last step, number 5, says make any substitution, solve for B. Well, the substitution I need to make here is for the total current. If, back to this because it's a better picture than I drew on the blackboard there. But let's see, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. Looks like you've got 8 wires, if I counted those right, passing through my path. And it's even, if I hold it still long enough, it might even focus. Did a minute ago. There we go. So the current in one of those windings is what you would get on an ammeter, okay? If you had an ammeter in the circuit in series with this coil, and if that ammeter read 3 amps, just to make up a number, well, that 3 amps passes through this rectangle 8 times, assuming I counted those correctly, which I'm not completely certain of, but you get the idea anyhow. So if each strand of wire carries 3 amps, and you've got 8 strands of wire passing through the rectangle, 8 times 3, you've got 24 amps for the total current passing through this path that I've been considering here. Or in more general terms, if the rectangle contains n turns, then the total current passing through it is I times N. And so I total is equal to I times N, where I is the reading you would get off of a meter that's in series with this coil. Rearranging it a little bit. There's the magnetic field inside the coil. Now, one more problem to mop up here before I've got something I can draw my box around. If this is truly an infinitely long coil, then N is infinity and L is infinity. So we have here infinity divided by infinity, which is just as undefined as 0 over 0 would be. Let's instead introduce a lowercase n to stand for the number of turns per unit length. How many windings are there per meter? That would be finite. And so the field of an infinite solenoid is this fundamental constant mu naught times the current in the coil times the number of windings per unit length. And that's the version that's in your textbook. Actually, what I put on the formula sheet is this version here that's just above it. If you have, because sometimes I have this practical streak. I don't know if that makes me a bad physicist. It's like almost an engineer sometimes. But yeah, in the real world, you're not actually going to find an infinite solenoid. It'll be a finite coil. It'll have some finite number of turns and have some finite length. And when you stick those numbers into this will give you the magnetic field as long as you're not too close to the ends. And so kind of looking at it that way, I put this on your formula sheet as the magnetic field of a solenoid. But like I said, if it's truly an infinite solenoid, you have to go with this version here. Also on formula sheet, I'm not going to take the time to show how these follow from Ampere's law. The field of a toroidal coil, the derivation for that is fairly similar to what I just went through. A toroid is a donut, okay? You have a donut and you just take your wire and you go down through the hole and up around the outside and down through the hole and up around the outside. And you work your way around the donut like that, and that's a toroidal coil. It's basically just a solenoid that's been bent around so that the ends come together, and it's mu naught IN over the circumference of the toroid. And then the other one that's on there is a flat coil. You've already used that formula once when we did the E over M lab. You had a short coil, short compared to its diameter, on either side of that bulb where you could see the electron beam. And anyhow, Ampere's law is thought of as being the fundamental relationship, fundamental equation of magnetostatics. And either sometimes by not quite such a direct process, but one way or another, any magnetic field, any unchanging, steady magnetic field can be derived from Ampere's law, as I've shown with a couple of examples, and I will with a couple more here. For my next trick, looks like we're down to problem number 3. So something with some specific numbers in it this time. students quite often like that better than some more general problem that's all full of letters. So you've got an ion beam, which is shooting right, this is by this hand, it's shooting right out of the page toward you. So you got all these ions kind of going along like that. And this, it's a big ion beam. As ion beams go, it's got a 5-centimeter radius. And our job is to determine the magnetic field at point A and also at point C. I used to do point B also, but I was trying to save a couple of minutes and it was kind of repetitive. So we'll just do A and C. So once again, we have to start out by picking a path. Here's the beam. Just like the picture in the handout there, the ions are flowing toward you out of the page. Well, this is not terribly different than the field of a wire, okay? I did that demonstration just before the break where there was the little piece of vertical wire mounted in the little box, and I had the compass, the magnetic compass sitting next to it, and you could see that anywhere I put the compass, it pointed in a direction tangent to a circle around that wire. Well, this is a similar kind of thing. Once again, the field lines are going to be circular, okay, centered on the center of the beam. So a good choice, well, in general, you kind of take advantage of the symmetry involved. In problem number 1, where you had a wire with a circular cross section, we chose a path that was a circle. In number 2, the solenoid that I just did a little earlier today, the field lines are straight. And so a good choice was a path with straight sides, a rectangle. Well, here, once again, we have sort of a circular symmetry. So once again, a good choice for a path will be a circle. Yeah, that doesn't really look much like a circle at all, but cut me a little slack. Maybe that should be a little higher. Oh, I guess that's good enough. Anyhow, that's my path. It has a radius of 2 centimeters. Because the point where you want to know the field should lie on the path. And for part A of the question, we're supposed to find the magnetic field, or the magnitude of the field, at point A. Point A is 2 centimeters from the center, so my path should be 2 centimeters from the center. Now, if you take this path and divide it up into many infinitesimal pieces, each with a length ds. Well, there's a rather enlarged picture of one of those little ds's. The magnetic field, as I said, circles around the center. So at this particular point here, its direction is tangent to that circle. And the point I'm trying to illustrate at the moment is that at any point along this path, B and ds have the same direction. And so theta is 0 degrees. Cosine of theta would be 1. So no need to divide it up into several parts like I did with number 2. B is constant all the way along the path, theta is all the way along the path, so we can just say that the strength of the field times the length of the path times the cosine factor, which is just equal to 1, like I was saying a minute ago, is equal to mu naught times the amount of current, not the total current in the beam, but the amount of current that passes through the interior of my path. All of those ions that are flowing along out here, they don't count. It's the current inside the path that's proportional to the field along the path. When you're talking about a circular path, its length would be the circumference of the circle. In other words, if I've got an ant running around on my blackboard here, how far does the ant have to walk to get back to its starting point? As for how much current passes through the interior of that path, well, the bigger the path, the more amps are going to go through it. And so if I look at the current density, how many amps per square meter are there, times how many square meters are included within the path, amps per square meter times square meters would give me amps. The question gives me the current density, 3 times 10 to the 5th amps per square meter. So I've got a number to fill in for this. A for amps here, A for area there. Hopefully nobody's messed up by that. The area, well, it's a circle that I've chosen. The area enclosed within a circle is pi r squared. So we've got 377 amps going through that thing. Might as well fill in some numbers over here. Maybe I should have done that before. Circumference 2 pi r, the radius is 0.02 of a meter, so 0.1257 of a meter is the circumference of the circle. So the length of the path goes in for S. The 377 amps goes in for I. You can look up mu naught on your reference handout, 4 pi times 10 to the negative 7 when you're measuring in SI units. So I know everything except B, and as soon as I make myself a place to write it down, I'll have the answer. So you multiply those two things together and you divide by the other thing, and that's 2 zeros and a 377. The SI unit, of course, if you're in the middle of a test, you can look this up on your reference handout. There's that table of units at the end, but the SI unit for a magnetic field is a Tesla. So then the other half of the question is to find the magnetic field at point C, which is outside. Oh, incidentally, if anybody feels like a little bit of extra practice, I do have the field at point B written here. I might as well mention it. 0.00754 of a Tesla is the field. See, it's stronger at point B because the path is bigger. There's more amps going through it. Point C is a little different because it's outside the beam rather than inside of it. So let me start out again with a sketch. Okay, so once again, our path is a circle concentric with the cross section of the beam there. Once again, B times the length of the path. Probably ought to use brackets. Once again, the length of the path is 2 pi r. Probably ought to label that. That comes out 0.377 of a meter. I use the radius of the path because I'm calculating the length of the path. Over here on the other side, the field times the length of the path equals mu naught times the amount of current passing through the path. Just like in the first part of the problem, the current passing through the path is the current density times the area, but see, in part A, it was the same radius in both places. 0.02 in the one spot, 0.02 in the other spot. Here, it's not. Here, I use the radius of the path because I need to calculate the length of the path. But over here, I don't need all of the area enclosed within the path because in this last outer centimeter here, there's no ions there. The current is all within that first 5 centimeters. So I need to care amps per square meter times how many square meters contain any amps. That's why I need 0.05 here rather than 0.06. So the area containing the current times the current density would equal the current. And so altogether, and this would be the total current in the entire beam, the whole beam is inside of my path this time, 2,356. That's a lot of amps. So you multiply and you divide, and this time .85 milliteslas, if you prefer. Number 4 says, now you try this. Okay, we've done the same thing a few times before in this course where I've said, after a certain point, there isn't any more to be gained by you sitting there and watching me do another example. Why don't you try it out and see if you're any good at this? So if there was anybody in the room besides me, I would hit pause on the recording at this point and maybe go around the room, make a few suggestions before I went over it on the blackboard here. But as things are, you should hit pause at this point and work on number 4 for a little while. And then when you unpause it, I'll go over it and we'll see if you understand this stuff. And of course, anytime you get some questions, you can email me, or if you happen to catch me in my office, you can call me on the phone. Or actually, as I understand it, you are not prohibited from coming to class. You can actually come here and talk to me if you're not afraid somebody's going to give you leprosy or something like that. So right here, pause it. Okay, now you've unpaused it, and I will go over number 4. It's kind of similar to number 3 in that, once again, you've got cylindrical symmetry for the shape of the current here. It's just that instead of a uniformly distributed current all over this space here, it's flowing through a pipe, presumably a very thin pipe. So all of the current is at the outside edge, and what you've got inside of it's just a lot of nothingness. So very similar to number 3 that I just went through. I quite often do this when I'm going to have students work on a problem for practice, is I'll do one that's kind of like it just before that. Number 4 is kind of like number 3. So part A, cross-sectional view of the pipe. Current is once again flowing out of the page toward you through the walls of this piece of tubing. I'll put some dots on there to represent the current coming toward you. And that's what labeled current, that's 5 amps. Part A asks about a point inside the pipe. The pipe has a radius of 1 centimeter, and we're interested in the field 3/4 of a centimeter from the center. So the path I use should have a radius of 3/4 of a centimeter. Ampere's law says strength times the length, mu naught, times the amount of current that passes through this dashed loop that I've drawn here. And I suppose I should mention that there's no need to integrate. Most of these problems are set up that way because of the symmetry here. If I took this picture and I rotated it 41 degrees, you would never know. So every point along that path is in exactly the same situation as every other point along that path. And so the strength of the field is the same everywhere along that path. So it's just B times S without having to integrate. Hopefully you didn't invest a lot of time doing some lengthy calculation, because in part A, the answer is just 0. Because the current flowing through the interior of that loop, all the current here is outside of the loop. There isn't a single electron that passes through the interior of my path that I've chosen. So because I equals 0, and because the length of the path is not 0, that means that B must be 0. There is no magnetic field anywhere on the inside because there is no current in there. Part B, this time we're interested in a point that's outside of the pipe. This time, really, it's just a rerun of the first example I did, where we found the magnetic field of a straight wire. Well, when you're on the outside of it, what's the difference if the wire is hollow or solid? You know, if it was solid, we'd call it a wire, and this time it's hollow, so it's a piece of pipe. Either way, well, I'll write out the details, but it's just a rerun of example number 1. B times S is equal to mu naught times, like I said before, current through the loop. In part A, none of the current went through the loop. In part B, all of the current passes through the interior of the loop. So I'm going to stick in 5 amps for that. Time to move the camera. So you look up mu naught in the usual place and you fill in the radius of the path. 1¼ centimeters is 0.0125 of a meter. Of course, if you wanted to get fancy, it would simplify the calculations a little bit if you noticed that this 2 pi here and this 4 pi there cancel and just leave you with a 2 here. You could just say B times the radius equals 2 times 10 to the negative 7 times the 5 amps. That would save you a few keystrokes. Not a bad idea, but I wrote it out this way because I was trying to think like a student, I guess. Anyhow, you fill in all those numbers, and if you don't make any mistakes with the math, if you don't like such tiny numbers, maybe you call it 80 microteslas. Let's see, we've still got like about 7 or 8 minutes. So I think we can do one more. Number 5 is not a problem where you start with Ampere's law. You know, you start with first principles and derives something for a more specific thing. Rather, number 5 is a superposition problem. What it does is it takes the formula for the field of a straight wire, which was the answer to problem number 1, and it says, what if you've got 2 straight wires? Well, superposing 2 magnetic fields is the same as superposing 2 electric fields like we did earlier in the course. You have to find the field vector from the one wire, and you have to find the field vector from the other wire, and you add them together. Find the vector sum. So that's kind of the big picture on number 5, and details go like this. Should probably come back over here. Let me redraw this from a different point of view, okay? What if here's the problem, or yeah, there we go, focus. What if you were over here looking at it from this direction, okay? So if you're on the right-hand side of the picture, kind of looking at these wires like this, well, that's where I put that. You've got these 2 wires that I called C and D. And if I'm over here on the right-hand side, I should probably label this. Right end view. Focus, thank you. Like it heard me. If you're over here on the right side of the picture, then the current in wire C is flowing, so it's flowing toward me, and the wire on the bottom that I call D, it's flowing away from me. That one gets an X. And as far as which direction is which, well, like it shows there in the picture, the sheet of paper is the XY plane. the z-axis sticks out that way. Well, if I'm looking at it from the right-hand end like this, it would help if I turned around. So you're looking at it like that. So the y-axis is toward the top and the z-axis is toward the left. So y is that way, z is that way, and x is perpendicular to the plane of the blackboard when you look at it from that point of view. And you don't have to do this, but I thought it would be useful to look at it from an angle where the magnetic field lies in the plane of the picture instead of it being a bunch of X's and dots. So for for both of them, the magnetic field circles around it. For C, since the current is out of the page, that means the field lines, well, in particular, because the question asks, what's the field halfway in between there? So at this point in the middle right here that we're interested in, the field is pointing that way. And again, halfway between the wires, which would be up here in this picture, right-hand rule. Your thumb points along the current, your fingers wrap around in the direction of the field lines. Up here, that would be pointing that way. So at this point here that the question asks about, the field from C points in the negative z direction, and the field from D points in the negative z direction. And so all we have to do is figure out each one of those and add them together. Both of them are given by the expression that was the answer to problem number 1. So for C, there's 10 amps in that wire, and it's located 5 millimeters from the point we're interested in. And a few moments with a calculator. Again, it's probably a little easier to punch it up if you notice that 4 pi over 2 pi is just equal to 2. So 2 times 10 to the negative 7 times 10 divided by 0.005. I would just do that. So the contribution from the one wire is 4 times 10 to the negative 4 Teslas. 4 Gausses, if you'd rather look at it that way, or in terms of more modern units, 0.4 of a millitesla. The other wire has 7 amps in it. Same distance away. And that one comes out 2.8. In other words, 0.28 of a millitesla. And then the superposition principle says, find the vector sum. Well, they both point in the same direction, so that's just adding them. 0.28 plus 0.4, 0.68 of a millitesla in the negative K direction. And that's the answer. And that's about 55 or 56 minutes worth of stuff. We'll call that enough for today. Kind of miss you guys. It's too quiet here.